Good afternoon, everyone. I'm Jingrong. I'm a PhD student from Duke. Today, I'm glad to talk about our work, NetHint, an interactive mechanism between a cloud tenant and its provider to jointly enhance application performance. This is a joint work with my colleagues at Duke, UC Berkeley, and the University of Washington. Data-intensive applications are increasingly moving to the cloud for resource elasticity, performance, security, and ease of management. The application performance is so important that the cloud provider have put tremendous effort into improving their cloud networks. The cloud is transparent in terms of its CPU and memory configurations, but the network is a black box. Today's cloud only provides a black box network abstraction. It's a black box model in a sense that some information is hidden. For example, here's a typical depiction. In this picture, all the instances, all the virtual machines of the tenant are connected to the cloud fabric. And each instance has a bandwidth of, for example, no more than 25 gigabits per second. This abstraction is simple. However, tenants only have minimal knowledge about their network performance. That is, a tenant do not know their link layer topology, which reveals which set of instances have better locality. For example, they're in the same rack. Moreover, tenants are also unaware of the instantaneous available bandwidth because it does not know other tenants who are sharing the same network. For example, in this picture, the tenant A alone can get 25 gigabits per second bandwidth. But when it shares with two other flows in the network, it can only get 1/3 of the total bandwidth. This black box model has been worked well. However, it is no longer sufficient for today's data-intensive applications. Data-intensive applications today have the ability to adapt their traffic patterns. Taking broadcasting as an example, which is an important communication thematic in reinforcement learning and ensemble model serving. In such a simple dumbbell topology of 4 nodes, VMA wants to broadcast data to VM B, C, and D. For an application controller or scheduler, there are several possible ways to build a broadcast tree. For example, VMA can first send data to B, then C, then D. There are also other possible options to do the broadcast. And this example here is actually similar to the classic example in traditional layer 4 multicast work, where people build different overlays to do the multicast. Data-intensive applications also have the incentive to adapt the traffic. For the same dumbbell topology, now consider that all the links have the bidirectional bandwidth of 1 unit. In the meantime, VMD has an upstream traffic, background traffic that takes 1/4 of the total bandwidth. If the application scheduler does not know anything about their network, it is possible for VMA to first send data to B, then C, then D. But this broadcast tree causes heavy congestion on the cross-rack link because it has to cross the inter-rack link twice. So each flow only has the half of the link bandwidth, which results in a broadcast completion time of 2 units. Think about it. If we can know the network topology of these virtual machines, we can make the broadcast tree cross the rack for a minimal number of times. That is, for example, A to C, C to D, and D to B. The bottleneck now becomes the upstream of VMD. The broadcast time improves from 2 to 4/3 time units. Alternatively, if we also know the available bandwidth of each virtual machine, we can build a broadcast tree from A to C, C to B, and B to D, which also avoids the congested link. So in this case, it can achieve the broadcast finish time of 1 unit, which is optimal. By choosing a different broadcast strategy, data-intensive applications can enhance communication performance, so they have the incentive to adapt their traffic. Note that these bandwidth and topology information are available in a private cluster or a controlled environment, but they are not available in today's cloud. As a result, today's black box networking abstraction and the adaptiveness of data-intensive applications together create a fundamental mismatch. This mismatch misses an important opportunity to optimize the application performance. So the question is, can we address the mismatch without changing today's black box abstraction? One way to address the mismatch is to do user probing. That is, we let the tenant do extensive traffic probing to profile their network performance. This has actually already been explored by many previous studies. However, user probing is costly because every application has to send probe traffic for itself, and this is not optimal from a global view. User probing is also slow because it will delay the start of the application traffic. The idea of user probing has been rejected in the past, and we reject it again. Then, how about we solve it in a white box way? In this paper, NetHint also considers a white box solution. But let's first explore a Strawman solution. The idea of white box is to let the cloud provider expose some useful information to the tenant. For example, the topology information might be useful for applications to make topology-aware scheduling decisions. Then we can let the provider reveal the VM placement in the physical network. The cloud provider can also tell the tenant how much bandwidth it can get, so that the tenant's applications can update its transfer schedule based on the bandwidth information. But to provide the bandwidth information, the provider needs to monitor the network conditions and collect network metrics constantly. It also needs to calculate the available bandwidth for each tenant individually. This causes several problems. First, directly exposing the VM placement and available bandwidth of the link can raise security concerns because they may leak information of other tenants. Second, the communication pattern of different tenants can change frequently, and recalculation for each tenant query is expensive. To address those problems, we propose NetHint. NetHint is an interactive mechanism between a cloud tenant and its provider to jointly enhance application performance. Contrary to the naive white box approach to directly expose accurate information, the key idea of NetHint is to only provide a hint, which is an indirect indication of the underlying network characteristics. For NetHint to work, a NetHint service first collects the network characteristics. Then the tenant application queries the hint from the NetHint service. Finally, the application adapts their traffic and creates some new transfer schedules based on the hint and their own demands. A new transfer schedule can further change the network characteristics. So the NetHint service collects the network metrics periodically and provides new hints to its tenants. For NetHint to work, we need to answer 3 key questions. First, what hints to provide, and how to provide hints with low cost, and how should the application adapt their traffic based on the hints. Next, we will go through these questions. So the first question, what hints to provide? First, we observe that oversubscription is prevalent in modern data centers, and machines under the same rack usually have better locality. Therefore, we provide a hierarchical virtual topology to capture this locality information. This virtual topology describes the network as a tree data structure. For example, in our testbed, we only have oversubscription at the rack layer, so we provide a 2-layer tree that abstracts the network as above the rack layer. The leaf nodes of the tree represents a tenant's virtual machines. A link in the tree can represent one or more physical links. This tree does not reveal racks or servers where tenants does not have virtual machines on, but it can reflect the oversubscription and the locality of the tenant's own instances. With this virtual topology, the applications can easily make locality-aware scheduling decisions, and the provider still controls what information to expose to its tenants. Second, apart from providing the virtual topology, NetHint also allows applications to react to the hotspots in the network by providing the link utilization within each virtual topology. But describing the network utilization requires some techniques. First, we can simply report the total bandwidth on each link. Next, consider how much bandwidth a VM can get. It not only depends on the current status of the network, it also depends on how many flows an application wants to start and how these flows will share the network with other flows. If an application decides to start a different number of flows, it can get a different bandwidth. To handle this problem, one option is to tell the statics of all other flows to the tenant. This is not good because it leaks information of other tenants. Another option is to report the residual bandwidth on each link. This is aggregating information and does not leak information of other tenants in most cases, but this solution does not work either because we do not know how the flow will share the network with other flows. So only providing the total and residual bandwidth is not enough. To tackle this challenge, NetHint also provides an extra information, the number of competing flows sharing the same link. With this extra information, we can estimate the available bandwidth more accurately, and you can check the paper for the detailed estimation. For the second question, how to provide hints with low cost, NetHint deploys the daemon on each physical machine and collects the network metrics periodically. Different from user probing, the collected network information can be used for all tenants, so there is no extra computation cost for each single tenant. To avoid the full mesh communication between all the physical machines to exchange the network metrics, we employ a two-level all-gather approach. That is, we just need a rack-level all-gather. We can aggregate the information within the rack and select just one representative under each rack to run the OTO traffic. This hierarchical all-gather is a common solution in traditional overlay works. For the information update period, there is a trade-off between the timeliness of the hint and the communication cost. To strike a balance, we set the information update period to 100 milliseconds. We evaluate the overhead of NetHint's monitoring plan on a large scale. Since we only have 6 machines, we use each CPU core in our testbed to emulate a rack. The result shows that the CPU time and memory footprint of NetHint server are both very small. And the latency to collect network information across 240 racks is around 10 milliseconds, which is a magnitude lower than 100 milliseconds collection period in our testbed. The third question, how should the application adapt their transfer schedules? To answer this question, we classify a broad set of data-intensive applications into 2 categories, the collective communication and task placement. And for each category, we design a simple heuristics to use the hint and make scheduling decisions. And they turned out to be very good heuristics. They're very simple and effective. We encourage you to read the paper for details. There were also several other things to consider in the loop. For example, applications can take extra time to calculate new transfer schedules. A network can be highly dynamic, so the hint can be stale in some cases. How to mitigate the impact of the stale hints? Further, there could be potential bandwidth estimation errors. And some applications can potentially do conflicting scheduling decisions and cause herd behavior. How do they affect application performance? We also encourage you to check our paper to find these answers. We evaluate NetHint on a small but right testbed and in large-scale simulations. The network topology in both the testbed and the simulation has an oversubscription ratio of 3. We compare NetHint with 2 baselines, not using any network information, and user probing. For user probing, if the tenant has n hosts, the user probing runs in n/2 rounds, where each round's latency is either the latency to send 10,000 packets or 1 second, whichever is smaller. We evaluate NetHint how much performance gain NetHint can provide. These 3 figures are the CDFs of the speedup of communication finish time versus not using network information. The black vertical line here means the speedup is 1.0, which represents the baseline of no information. We use the same workloads as previous papers. And for each kind of workload, we run 50 to 100 jobs and show the average speed up to no information across all the jobs. The brighter the curve, the better the performance. The result shows that NetHint can outperform no information by 54%, 30%, and 14% in completion time on these workloads. This is because applications using NetHint can schedule with both bandwidth and topology information to avoid congested links. NetHint also outperforms user probing. This is because collecting hints is more lightweight than each application individually do probing. We have also done simulations on a large scale, and we have observed similar results. For more results, please check our paper. To summarize, we identified that the black box networking abstraction and the adaptiveness of data-intensive applications together create a mismatch. And we found that just a little hint from the provider and some simple scheduling heuristics can be useful for improving application performance. We present NetHint and show improvements on various workloads. NetHint is also open source. Thank you for listening. I'm happy to take any questions.